Hi, everyone. Let's see. So the first question looks like is last week the group of Jianwei Pan and Xiaoyang Liu announced quantum supremacy using photonics. So what did this show and what did it not show? Uh, Unfortunately, the truth is that we don't know yet. Uh, so they put out this paper last week with a remarkable experiment involving boson sampling, which means sending a bunch of photons through a network of beam splitters and then measuring them. And they were able to detect about, on average, about 50 photons with each detection. And this took about 3 minutes. And their claim is that simulating this with a classical computer would take about 2 billion years, at least using the algorithms that they know. So if true, this would be the second achievement of quantum supremacy following Google's announcement from a year ago using its superconducting qubits. Um, and basically, what happened is that as soon as this paper was announced, skeptics started taking a crack at it. And there were some strange bedfellows here from Gil Kalai, who doesn't believe in quantum computing at all, to the Google team, which would also like to, has some competitive interest here. But this is exactly what should be happening. People are now trying to see, could we reproduce these results with a classical computer? Could we exploit the noise and the imperfections in the experiment to do it faster than was claimed? And so it's a very technical discussion. I was just involved in that discussion earlier today. I mean, the situation is changing from one day to the next. But if let me just say, if the experiment turns out to have shown quantum interference among 50 or so photons, then what that would show is that first of all, you can achieve quantum supremacy not only using superconducting qubits, but also using photonics, which is a completely different technological route. And I do think that quantum supremacy is something that's important enough that it needs to be verified more than once by different teams, using different platforms. So that's great. Um, it would also show that you can answer the objection that IBM raised to Google's quantum supremacy experiment just a few weeks after it came out. So those of you who remember, what IBM said was that, well, we could simulate what Google did with its quantum computer if we used literally the biggest supercomputer on Earth, which is called Summit, and which fills the area of two basketball courts. Okay, but they said if you had a big enough supercomputer, you could just take the entire probability distribution over the outputs of Google's chip. Okay, and to be clear, we are talking about 2 to the 53 power possible outputs for a 53 qubit machine. Okay, that's about 9 quadrillion. But it so happens that there are one or two supercomputers on the planet with enough hundreds of petabytes of hard disk space that they could just store 9 quadrillion probabilities. And so if you spend a few days to calculate them, then once you had done that, then you could generate as many samples as you wanted from the supposedly hard distribution. Now, the Chinese experiment, the USTC experiment, if it works, then it should be resistant against that kind of attack. And the reason is that there are about 10 to the 30th power possible output states, rather than just 10 to the 16th power. Okay, so even though each specific probability is maybe about as hard as to compute as it was in Google's experiment. Maybe easier, maybe harder. We're not sure. In any case, there are many, many more outputs. So the strategy of caching all of them in a hard disk wouldn't work. So that's the advantage. But as for whether the noise in the experiment was high enough to preclude quantum supremacy, that we're going to have to see. And it's important for everyone to understand that quantum supremacy is not like landing on the moon. It is more like proposing a new cryptographic code, right? Where one person has to put out the claim, and then the whole community has to work together to see if they can shoot down that claim. And only if they fail to do that do we have confidence in the original claim. Okay, so this is exactly the way that the process is supposed to happen. But even skeptics, are very impressed by what the USDC team managed to achieve at a hardware level. Certainly I did not expect that by 2020 people would have integrated these hundreds of beam splitters and hundreds of photon sources and detectors in order to do a boson sampling experiment at this scale. So I'm very happy about that. Yeah. Let's see. Next question is between last year's Q2B and this one, what has surprised you the most in the field of quantum computing? Well, that's a tough one. I mean, it might just be, the achievement of 50 photon boson sampling that we were just talking about. Um, I would have to think about what else. There was some remarkable work over the past year in understanding the power of the quantum adiabatic algorithm. The initial work by Matt Hastings and follow-up work by Umesh Vazirani and others. They have now shown at least theoretical examples where the quantum adiabatic algorithm can solve a certain black box problem and find the global minimum of a black box function in polynomial time, whereas any classical algorithm will provably need exponential time to solve the same problem, have to make exponentially many queries to the black box. That was an open problem for about 20 years. I didn't expect it to get solved. I'm delighted about that. Um, Another thing that surprised me a lot was that has to do with copy protected quantum software. Okay, so there's been a question. As far as I know, I first raised it around 2003, and then again in a paper in 2009. The question was, could you have a quantum state that you would just give to someone? And we're talking about a far future where you can maintain an entangled quantum state of hundreds of qubits for months or however long, but such that you could measure this state in a way that would let you compute a function, on any input of your choice, but you would not be able to make more copies of the state. And in fact, you couldn't use it to make any other states that would let anyone else compute the same function. Okay, so this would be using quantum mechanics, especially using the no cloning principle of quantum mechanics to achieve copy protected software, which for better or worse has been a dream of software companies for a long time. So the question that I raised years ago was, is this possible for arbitrary functions? Can you take any class of functions and use quantum mechanics to basically make an uncopyable black box for that function so that no one could copy it, unless they could also have copied it by just feeding inputs to the black box and seeing what the outputs were. And I showed how to do this for some very special functions, or gave candidate ways to do that. But we didn't know if it could be done for arbitrary functions. My guess was yes. My guess was that it could be done, and this was a problem I gave out to many students. Now this year, it was proven that under some plausible cryptographic assumptions, the goal is impossible. So there are types of functions that cannot be quantumly copy protected. That was Rolando de Placa and others. There were two groups that proved this independently, and it uses some sophisticated tools, quantum fully homomorphic encryption, which was only just developed over the last couple of years, but it's a very, very clever argument. And that was also a development that surprised me this year. Okay, in your opinion, how much of the community's effort should be spent on increasing accessibility to low-level interfacing of quantum devices, like quantum assembly language and circuit programming, versus accessibility to high-level interfacing and compilers? Um, I think that uh, you know, these things are all going to proceed in parallel, right? I don't feel like we are suffering right now from a shortage of quantum programming platforms or quantum programming languages. On the contrary, there is now a glut of such things, right? We are, and that's good that there are now so many options available for programming platforms. I mean, I think it all depends on what someone's goals are, right? In the early stages of this field, in the NISC era, for example, I think that people are going to want to have a lot of low-level control over the quantum circuits that they're building, because every gate matters, right? And every qubit matters. If you've only got 50 qubits available, or 70, or 100, if you've only got 20 or 30 or 50 layers of gates, well, then you don't really have a lot of wiggle room for high level abstractions, right? You're just thrilled if you can get something to work at all. I think further in the future, if we do get to an era of thousands of qubits or even millions of qubits that are error corrected, then that is the time when it makes sense to use a higher level abstractions, to use compilers, um, where the quantum programmer would not have to necessarily think in terms of the individual qubits and gates. Um, of course, I hope we reach that era. Okay, but in the meantime, this was not true, even 5 or 10 years ago. But I would say that like a full programming stack, a full set of tools for quantum development, now does exist, and people can get started trying at sort of whatever level of abstraction they're most comfortable with. Do okay? The question is, do you have confidence in the proposed post-quantum crypto system? Okay, well, I don't have absolute confidence in any, certainly in any public key crypto system, right? All private key crypto systems, symmetric key crypto systems. Those I think one can have a great deal of confidence in, because breaking a sort of generic scrambling function like a DES or AES, that seems almost as shocking as proving P equals NP, right? Uh, but for public key crypto systems like RSA, Diffie-Hellman, elliptic curve systems, lattice-based systems, all of these are based on very specific mathematical problems, that have a lot of structure, right? And structure is wonderful if you can exploit it for cryptography, as we've learned how to do since the 1970s. But the other edge of that is that it opens up attacks. Okay? It means that someone could come up with a clever algorithm to exploit that structure, just like Shor did when he discovered his quantum algorithm for factoring. Now, regarding the post-quantum crypto systems, such as the lattice-based systems, or the systems based on LWE, or isogenies of elliptic curves, I wouldn't say that I have complete confidence in any of them, but at least for the lattice and LWE systems, the others I don't understand as well. But the lattice and LWE systems, I would say that those things have been around for 25 years by now. A lot of smart people have thought about them. They have gotten stuck designing either classical or quantum algorithms to break them. We understand something about the reasons why they've gotten stuck. And so I think that one can have almost the same kind of confidence in those as one had in RSA or Diffie-Hellman in the security of those against classical attacks. In fact, some people might even say that we should have more confidence in these lattice-based systems than we had in RSA or in Diffie-Hellman, just because the lattice systems are somehow based on more generic, less structured mathematical problems. Okay, question is, how will our current software engineering approaches need to evolve to support projects that rely on quantum computing? Um, well, the way that I think about it is that quantum computing is a special purpose accelerator, for certain very special applications, that are able to make use of it. Right. Initially, problems involving physical simulation, at the micro scale. Chemistry, material science, things like that. Breaking cryptography, of course, and achieving Grover type speedups for lots of optimization and machine learning problems, and possibly achieving some other speedups for machine learning or for other problems. But those things are still being studied. So in terms of software engineering, a good way to think about programming for a quantum computer, is maybe is analogous to programming that would take advantage of a graphics card, right, or some other special piece of hardware, that a computer would have for special purposes. So there will need to be programmers who actually understand this, who specialize in it. That will not need to be all or even most programmers, right? And this is the whole point of a lot of these software frameworks that people have been developing to try to abstract away the parts of a software project that could make use of quantum tools, um, and so that sort of the programmers of the other parts of your system would not need to know about them. But I should say I am just a theoretical computer scientist. I'm not a software engineer, but I'm not an expert. But those are what thoughts I have. Okay, so the next question is, what do you think about the computational time efficiency of algorithms in the quantum machine learning domain for theoretical and practical computational problems like variational circuits in the future versus their classical approaches? That's a complicated question with a lot of clauses on it. Uh, but okay, so let me speak first about quantum machine learning. Um, I think that the huge challenge still remains to sort of come up with what are the killer examples for quantum machine learning, where the time complexity will be a lot less than what we could achieve with any classical algorithm. Right? As some people know, there was a nice candidate for an exponential speedup, the Karanides-Prakash algorithm, and that was dequantized a couple of years ago by an undergraduate, Ewin Tang, who was working with me. And over the last couple of years, what has happened is that building on Ewin's breakthrough, a lot of other quantum machine learning algorithms have been dequantized, meaning that people have discovered that for the limited information that that algorithm is able to give you, one can design a classical algorithm with only a polynomially larger time complexity that gives you that same information. Um, Now, often this is very non-trivial. Often the classical algorithm was only discovered because of the quantum algorithm being discovered first. So this leads to this theme of quantum-inspired classical algorithms. But I am hopeful that someone will figure out how to get an exponential quantum speed up for a machine learning problem, more than the Grover speed up, in a way that will resist dequantization, that will resist the kind of thing that Ewing did. But that's still very much an active research area. I hope that in just a couple of years we will know more. Now, there was also something in the question, I don't see it in front of me anymore, about variational algorithms. Um, about variational algorithms. I'm not sure. I mean, I'm not sure if that much has changed there within the last year. But the QAOA, I am worried that the amount of attention that sort of goes into that one algorithm, may be out of proportion to what we know about what success it is able to deliver. Right. I would say that to date, I'm not sure that we have even one example where it is clear that QAOA will outperform a classical algorithm or the best classical algorithm for a problem of practical interest. There were many valiant attempts to find such an example. Some of those attempts were then killed off. Um, but I mean, QAOA is an example of using the variational approach to try to solve classical problems. I think we don't know yet if there is any case where that is going to win. I am more optimistic about variational approaches, being used to solve quantum problems. Estimating the eigenvalue of the smallest eigenvalue of a Hamiltonian, learning about physical systems. Okay. What reference would you recommend for someone who wants to get started learning the basics of quantum mechanics? Well, that's a great question. I do have a book about this, Quantum Computing Since Democritus. Well, it's about a lot more than quantum computing. It's about a lot of other things too, but it's not for everyone. It takes a very idiosyncratic approach. There is, the Nielsen and Chuang textbook, which I'm actually using right now to prop up this laptop. So I don't want to take it out and show it. But Nielsen and Chuang is 20 years old, and yet it remains, in some sense, the standard reference for our field. And has a excellent introduction to the basics of quantum mechanics. But there are also lots of lecture notes that are available for free on the web. There are John Preskel's lecture notes. Those might have a little bit too much physics for people coming from a CS point background, but for physicists, they will just hit the spot. There are Umesh Vazirani's lecture notes. I have lecture notes from an undergraduate course that I teach called Intro to Quantum Information Science. You can find that on my homepage or my blog. And and the prerequisite for my undergraduate course is just linear algebra and complex numbers. There is no physics prerequisite whatsoever. Okay, and I really think that linear algebra and complex numbers is about all that you need. You can develop the basics of Bra and Ket notation, unitaries, density matrices, the Bloch sphere, and so on and so on. My set of lecture notes is just one example of something that does that. There are by now dozens of others, and so you can find the one that sort of best matches your personal learning style. Okay. Do you believe the timelines for broad quantum advantage and full fault tolerance are likely to arrive much earlier than what you might have thought a few years ago? Okay, well, maybe the word much is doing a lot of work there. I think that what have we seen within the last few years that might change someone's estimates? Well, most obviously, we have seen the demonstration of quantum computational supremacy by the group at Google, and now possibly we have also seen the demonstration of quantum supremacy using photonics by the group in China. So that was not obvious. I mean, I would say a few years ago we were hopeful that quantum supremacy might be achieved by now, but there are no guarantees in this business, right? And so the fact that it apparently has been achieved should cause us to, if we're Bayesians or whatever, it should cause us to, become a little bit more optimistic in our timelines compared to whatever they were previously. Uh, you know, Now, the big question, the you could say is when are we going to see truly useful quantum error correction and quantum fault tolerance? There are already some experiments that claim to get some net gain from the use of error correction. If you kind of squint at them, you can, maybe see that. But what we really want to see is computation being done on fault tolerantly encoded qubits in a way that does better, achieves a lower error than what you would have gotten by running the same computation on the purely unencoded qubits, right? And ideally, a big computation, ideally a useful one. So when is that coming? We still don't know, and that could be very, very hard, right? And certainly if you look at the overheads for fault tolerance, they are still much, much bigger than one would like them to be. Okay, and so it's a little bit like now you've gotten into space, you've gotten into orbit around the Earth. Maybe that's quantum supremacy. And then maybe quantum fault tolerance is like landing on the moon, right? But getting into low Earth orbit is a step toward the moon. It's certainly from an engineering standpoint, and so I think it should cause us to be at least somewhat more optimistic. Okay. Do you agree with Eric Schmidt's statement that scaling quantum computers from NISQ to large scale fault tolerant systems is largely an industrial problem and the solution is arriving within a decade? Okay, well, I don't know. I hope so. I am not in the business of making proclamations about, what has to arrive, what will arrive within a decade. If I were, I guess I wouldn't be an academic. I would, be an investor or maybe a business person and maybe even as wealthy as Eric Schmidt. Okay. But I think that we know a lot about what the engineering problems are that have to be solved in getting beyond the NISQ era, to the era of full fault tolerance. But at the same time, we are really just at the beginning of the NISQ era itself, right? It's been a year since the Google supremacy thing, which was sort of like the starting shot of the NISQ era, if you like. And most of that year, we've all been stuck at home because of COVID. Okay, so we really are just at the beginning of this. I think that I could easily see, at least 10 years just for sort of exploring what can be done in the NISQ era. And for getting to fault tolerance, I mean, clearly it is a huge industrial problem. Clearly, already we have seen that the expense of doing a cutting edge quantum computing experiment, or a scaling experiment, has exceeded what most universities can manage, right? And so, 10 years ago, the biggest experimental players, were you saw a lot of universities, right? Today, you see, Google, Microsoft, IBM, now Amazon, Honeywell, IonQ, and all the others who you heard from at this meeting. So, so there is an industrial problem, but I'm not ready to say that there's no more science to be done here. And in particular, it comes back to what I was saying earlier. But the overheads for fault tolerance, still look enormous. They still look like they're so enormous that they're going to kill off a lot of the quantum algorithms that we like, such as Grover's algorithm. They're going to negate the speed up from them, as some of the previous speakers here explained. unless we can discover a much better way to do fault tolerance with a much lower overhead. Some people hope that topological quantum computing could be that way, but it's possible that there are other ways that we just haven't that no one has thought of yet. And you can't invent write timelines or roadmaps for new ideas, right? As David Deutsch loves to emphasize, one of the founders of quantum computing, new ideas by their very nature are unpredictable. And I really hope that there will be a new idea that will just enormously cut down the overhead of fault tolerance. I mean, that could really make the difference between, fault tolerant quantum computing becoming practical in the next 10 years or 20 years and it not. Are you starting to see a significant uptick in quantum computing interest from computer science students? Um, so I would say that there is a lot of interest. I mean, I moved from MIT to UT Austin 4 years ago, and I have been teaching every year an undergraduate course, Intro to Quantum Information Science. The amount of interest, well, it was already high 4 years ago, but it's become even somewhat higher. I mean, you can easily get 80 students, per year, in a pretty advanced course, right? And not one that the students need to graduate. One that they're taking because they're interested in it. And I think that if you look over the time scale of 10 years or so, there is definitely more interest among CS students now than there was a decade ago, and I think some of the reasons for that are apparent. It's because now people see that there is all this excitement at large companies, at governments, and they see that people are finally starting to build systems that integrate a large number of qubits and that can start to do interesting things. Now, whether there is going to be a quantum computing industry to speak of for students to graduate into, whether there will be a pipeline, that will employ them, not just like a relatively small number who would get PhDs and become, research scientists, but a larger number of quantum computer developers. I think that remains to be seen. That a lot of that depends on what happens in the next decade. Okay, so 5 years ago, you wrote a great perspective. Oh, thank you. Pointing out that the known quantum machine learning algorithms still had some practical holes to be filled in, especially regarding input output bottlenecks. How have your views evolved since then, if at all? Well, frankly, the main thing that happened since I wrote that perspective article for Nature Physics 4 years ago was the mini revolution in dequantization of quantum machine learning algorithms. Right. So, Ewan Tang managed to dequantize this Karenides Prakash algorithm that was based on high dimensional linear algebra, and then building on that, people have since dequantized um, a bunch of other machine learning algorithms, typically ones that involve low rank matrices. Um, so, that is consistent with sort of what I warned could happen in that perspectives article, but, it makes it a lot more concrete, right? It makes people might not have listened to the worry before, but once the algorithms have been dequantized, then maybe they see the worry more. There have been new proposals in the meantime for quantum machine learning algorithms. So the area continues to evolve. But I think that the basic points that I made there, that you need, or were that you need an end-to-end application, right? It's not good enough to say, well, here is my quantum machine learning algorithm. Its output is a quantum state. And now how do you measure that quantum state to learn something of interest about your original problem? Well, that's not my job. I'm done, right? That's just you. That's just the end user's job to figure out how to measure the state. You can say that, you can write a paper saying that, but you do not then have a clear application of quantum computing to machine learning until somebody fills those holes in, until someone shows how to get the input data and encode it into a quantum state, how to measure the output state to learn something that you actually care about, and then also gives evidence that learning that same thing would be hard for a classical computer. Okay, so and none of what I wrote in that 2016 article was new, right? All of this was well known to the people who work in this field. But I'm glad that little article that I wrote, which I didn't think much of at the time, but it seems to have actually played a role in crystallizing people's thinking about this. So I'm gratified about that. Okay, overall, are you optimistic or pessimistic about commercial NISC applications? Um, I would say, I am hopeful that there will be at least some application. Uh, optimism or pessimism is always relative to a baseline, right? It's always relative to what your expectations were going in. And I think that if someone tells me that they were expecting that quantum, they were expecting that noisy quantum computers, in the NISC era, are going to revolutionize machine learning, revolutionize supply chain optimization, or even quantum simulation, all these other things, I would probably tell that person to be more pessimistic about it. Okay. But if someone came to me and they said, I am confident that there will be no application, you will not learn anything new about condensed matter physics or about chemistry or about any of it by playing around with these 100 or 200 qubit systems that are going to be coming online over the next decade, then I would probably encourage that person to be more optimistic. I think that we're going to see at least some applications, and these are problems where you might only need one big success to kind of justify the entire thing. Okay. Do I have any comment on quadratic speedups being dead on arrival and the need to go after larger gains like cubic? Is Grover's or Grover-like algorithms relevant or only good for edification? Okay, well, let me say this. If you took away Grover's algorithm, then you take away one of the main workhorses of quantum algorithms in its entirety. Okay, it is only for very, very few problems that we know or we are confident that we can get bigger speedups than the square root speedup of Grover. Okay, for most of the sort of workhorse problems that you would find in a computer science textbook, sort of either there's not a quantum speedup that we know, or if we know a the speed up is quadratic, it is that of Grover, or in many cases, it is subquadratic. Okay? It is, n to the 2/3 power or something of that kind. So if you take that away, then you really sweep the table pretty bare. And so, as I said, my hope is that eventually we get to the era of fault tolerance where there is where the distance between theory and practice is no longer so enormous. Okay, where you can take something a theoretical algorithm with a square root speed up and really see that it gets a square root speed up, right? But that is going to require a lot of progress on the hardware side, and almost certainly also progress in doing quantum fault tolerance more efficiently. Which is really one of the central problems of this entire field. Both for the theory and for the practice. But now that there was a mention in the question about cubic speedups, I wish we had more examples of that. I wish that we had more examples of polynomial quantum speedups that were bigger than the Grover speedup, like cubic or quartic. I'm aware of only a few rather exotic examples of speedups of that kind, and I would love it if we had more. Okay, are there any research areas related to quantum that you think that industry and government are neglecting that you think should get more attention? Um, well, I would point out that the whole theory of quantum computing, to a great extent, is built on top of the theory of classical computing, right? And over the last few years, we have seen an influx of funding for quantum computing, which is great. I met with the Senator Kamala Harris's staff when they were writing the National Quantum Initiative Act. I am happy that that passed, unanimously. I didn't even know that anything passed unanimously anymore in Congress. I'm glad that there is all this funding from the defense agencies, from also from companies. Um, but very, very little of that funding is sort of going to, if you like, the pillars that quantum computing sits on top of, right? One of those pillars is the classical, theory of computation, which is still mostly supported by the NSF, in the U.S. At a much, much lower level. Another pillar is, fundamental physics, right? Where you know, these days, some people who want to do fundamental physics or fundamental theoretical computer science will, get grants by writing in their application that, well, maybe it will be relevant for quantum computing. Okay, and so, in that roundabout way, they try to justify it. But, I do think that it's important, not just to sort of build the tower, but to make sure that the foundations are secure to continue supporting fundamental research in all of these areas that quantum computing grew out of and that it still very much draws upon. Okay, will we implement fault tolerant quantum computing with one of the error correcting codes that we have now, or will it be with a completely new one? Okay, well, I wish I knew. I mean, the fault tolerant, the error correcting codes that we know, such as the Kitaev surface code, the Bacon Shore code, the other codes that we know, they let us estimate numbers, right? So they give us a path forward that we could pursue. The problem is just that the numbers, for the existing fault tolerance schemes look kind of scary. Okay, and it could happen that nothing better gets discovered, and we just bite the bullet, and we eventually develop the hardware, to the point where we can implement those schemes. My guess would be that there will be modifications along the way, right? And if you look at what some of the companies are doing, who are trying to get to fault tolerance, whether that's Google or that's PsiQuantum or whoever else, they are, they're not just taking the theory off the shelf, right? They are taking the theory and they are adapting it to the needs of their hardware. And I expect that there will be improvements made to these codes. But whether there will be a completely new idea that just cuts the resource requirements by a couple orders of magnitude, well, alas, new ideas are inherently unpredictable, as David Deutsch reminds us. If we could predict them, then we would have them already. Yeah. Oh, okay. Okay. Anything else? Oh, all right. Do you expect ion traps to achieve quantum supremacy, or is there an obstruction for this hardware? I don't know of an obvious. Excuse me. Okay, yeah. All right, sure. I don't know of an obvious obstruction for ion traps, that would not apply to any of the other proposals. I am very hopeful that what was done with superconducting qubits and what was done with apparent, possibly now done with photonics as well, will now also be done with trapped ions. But part of it is motivation. The people building ion trap quantum computers have to want this, have to care about it, have to actually take it as a goal. Okay. All right. Well, thank you for all the questions. Hope you enjoyed.